Welcome to the third and final exhaustive portion of Module 1. Today we master traversal mechanics, connectedness thresholds, and the algebraic logic of graph topology. Let us define the fundamental mechanisms of movement within a graph. Navigation is governed by a hierarchy of constraints, starting with the walk. A walk is the most basic sequence, a finite alternating list of vertices and edges. Crucially, in a simple walk, both vertices and edges can be repeated an infinite number of times. It is movement without restriction. If we add a constraint to forbid the repetition of any edge, the walk becomes a trail. In a trail, you may visit a vertex multiple times, but you can never cross the same bridge twice. The most restricted open traversal is the path. A path strictly forbids the repetition of both vertices and edges, charting a unique, linear journey through the topology. When a traversal loops back to its starting point, we encounter closed structures. A circuit is a closed trail, where edges remain unique but the origin is revisited. A cycle is a perfectly closed path, where every vertex and edge is unique, appearing exactly once except for the starting node which acts as the terminus. This hierarchy establishes that every cycle is a circuit, and every path is a trail, yet the inverse logic remains mathematically false. To quantify these movements algebraically, we turn to the adjacency matrix A. An elegant theorem states that the number of walks of length are between vertex I and vertex j is exactly given by the entry in the ith row and jth column of the matrix A raised to the power r. We prove this by induction. The base case r equals 1 is trivial as the adjacency matrix itself lists edges. For the inductive step, a walk of length n plus 1 must reach an intermediate vertex k in n steps, followed by a final edge to vertex j. The total count is the summation over all intermediate nodes, which matches the definition of matrix multiplication, proving the theorem for all positive integers r. Now, let us analyze the structural integrity of the graph through connectedness. An undirected graph is connected if a valid path exists between every single pair of vertices, ensuring total global reachability. Conversely, a disconnected graph is fragmented into isolated regions known as components. Mathematically, a component is a maximal connected subgraph. Adding any more nodes would destroy its internal unity. In directed graphs, we distinguish between strongly connected, where paths are bidirectional and respect edge orientation, and weakly connected, where paths exist only if we ignore the direction of the edges. This leads us to a vital theorem regarding odd vertices. If a graph contains exactly two vertices with an odd degree, there is an absolute mathematical guarantee that a path exists joining them. Proof is by contradiction. If they resided in separate components, each component would contain exactly one odd vertex, violating the handshaking lemma. Thus they must be linked within the same connected structure. Finally, we calculate the extreme upper bounds of edge density. Theorem 2.3 states that a simple graph with n vertices and k components can have at most n-k times n-k plus 1 divided by 2 edges. The algebraic proof demonstrates that to maximize edges, one component must absorb as many vertices as possible to form a complete graph, while the remaining components are reduced to isolated nodes. Maximizing the sum of squares under linear constraints proves this boundary condition definitively, creating the most dense fragmented structure mathematically possible. This concludes the exhaustive exposition of Module 1. You have mastered the mechanics of movement, matrix enumeration, component fragmentation, and the algebraic limits of discrete modeling.